All right, hello everybody. We are going to work on more Lewis structures. This is the second part in my Lewis structures series. Where I was getting my examples from was the worksheet I had given out. The next example was number 5, methane. Methane has the formula CH4. Okay, now first we have to write our atoms on paper with our central atom in the center. Hydrogen cannot be a central atom, so carbon has to be our central atom. I'm going to put carbon in the middle, and I'm going to put the 4 hydrogens around it. Okay, have to do my accounting for valence electrons. So I have 1 carbon. It's bringing 4 valence electrons. Okay. I have 4 hydrogens. They're each bringing 4 valence electrons. That's a total of 8 valence electrons that need homes. Okay, next thing we need to do, every molecule needs to have some kind of covalent bond. So every hydrogen is going to get 1 bond into the central atom. Each bond uses up 2 valence electrons. So 2, 4, 6, 8. All right, and I've used up all of my valence electrons. You can see I have nothing left. I have to check my octet and my duet rule. So my hydrogens are complete with a duet. Each one has 1 bond, and each bond has 2 electrons. They're happy. They're very stable in this configuration. Looking at carbon, carbon has 2, 4, 6, 8, and that meets the octet rule. So everyone's happy here, and that would be our Lewis structure for methane. Okay, next on the list we have ammonia, NH3. Now, I want to take a moment to remind you that this is ammonia. It is not ammonium. Notice that this has no charge and 3 hydrogens, whereas ammonium has a positive 1 charge and 4 hydrogens. So just to be clear, that's not the one we're doing right now. Okay, so we're going to put nitrogen in the middle. It has to go in the middle because hydrogen cannot go in the middle. All right, we're going to do our accounting for electrons. We have 1 nitrogen. It brings 5 valence electrons. We have 3 hydrogens, each bringing 1 valence electron. So we have a total of 8 valence electrons that need homes. We're going to draw 1 bond from each terminal atom into the central atom. Each bond uses 2 electrons. So 2, 4, 6 have been used, leaving us with 2. So we need to find a home for these 2 valence electrons. So let's look at the octet and duet rule. We can see here that our hydrogens are fine. Each one of them has 2 valence electrons. And our nitrogen has 2, 4, 6. So it would like to have a set of 8. It needs 2 more. Well, I have 2 more. So these are going to go on as a lone pair on my central atom. Okay, and with that, everyone's happy. Hydrogens each have 2, and nitrogen has 2, 4, 6, 8. Okay, so the next one on your worksheet was silicon tetrachloride. So SiCl4. Let's do that one. And then I'm going to come back and let's talk about afterwards what happens when we have a charge. All right, silicon tetrachloride. My most electronegative element here is going to be chlorine. We always want the least electronegative on the inside. So we're going to put silicon on the inside, and we're going to surround it with our 4 chlorines. Okay, we'll start our accounting. We have 4 chlorines. Each one of them has 7 valence electrons. Of course, I know that because it's in group 7A on the periodic table. 4 times 7, we have 28. All right, I have 1 silicon, and silicon is in the oxygen group, the chalcogens. It's going to bring 6 valence electrons. Okay, so 1 times 6 gives us 6. 28 plus 6 give us 34 valence electrons. Okay, we can't have a molecule without a bond, so every terminal atom gets a bond into the central atom. Doing that, I used up 2, 4, 6, 8 of my electrons, leaving me with 26 valence electrons. Okay, now the rules say that I must start from the outside and work my way in, distributing my valence electrons. Okay, so I have 2, 4, 6 to give to that chlorine, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, I've used up 24 of my valence electrons, but still have 2 left. Now, don't panic. The rules for writing valence Lewis structures say that when the central atom is in period 3 or greater on the periodic table, it can form what's called an expanded octet. So, silicon is indeed in period 3 or greater on the periodic table, so I get to drop in this lone pair onto my central atom. Now you'll notice my chlorines have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. They're all happy with their octet. Silicon has 2, 4, 6, 8, 10. But again, it's called an expanded octet, and it is one of our exceptions. As long as the central atom is in period 3 or greater, it can accept more electrons than 8. All right, I want to move into what happens when you do have a charge and you need to notate that. So let's come back to ammonium. Ammonium is NH4 with a positive charge. Okay, well, of course, N has to go in the middle. H can never go in the middle. So I'm going to draw my N with 4 H's around it, and let's do our accounting. We have 1 nitrogen with 5 valence electrons. We have 4 hydrogens, each with 1 valence electron. All right, so that gives us 9. But this has a positive charge, and that means that we are missing one of our negative electrons. So I'm going to go ahead and subtract 1 electron from our accounting. So now we have 8 electrons that need homes. All right, can't have a molecule without bonds. Every terminal atom gets 1 bond into the central atom. 2, 4, 6, 8 are used up. I have nothing left. Let's check our octet and duet rule. Hydrogens are each happy with 2, and nitrogen has 2, 4, 6, 8, also an octet. So this is a stable arrangement, but we have to denote to our reader that we know that it has a missing electron that we accounted for here. And the way we do that is we surround our structure with giant square brackets, and then we put the charge symbol in there. So it's quite easy to do. The only difference here, we have to remember to account for either the missing or extra electrons. We have to surround our structure with giant brackets and give the charge symbol. Pretty easy. Okay, now I want to talk about what happens when you run out of electrons. Well, that's going to result in multiple bonds. So I'm going to take the compound CO2, carbon dioxide. Okay, I'm going to put the C in the middle, and the reason I'm putting the C in the middle is it is the least electronegative, and to be honest, we're going to find carbon because of its nice bonding properties in the center of a whole lot of molecules. In fact, that's why they have the entire study of organic chemistry. That's the study of molecules with carbon as their base, as their base or backbone. Okay, let's do some accounting. I have 1 carbon with its 4 valence electrons. I have 2 oxygens, each with their 6 valence electrons, and that gives me 12. So 4 and 12 make 16. Okay, we've got to find homes for our 16 valence electrons. What I'm going to do first is everybody gets a bond into the central atom, and that used up 4 out of my 16, leaving us 12 valence electrons. Okay, I'm going to do what the rules tell me. Start from the outside and work my way in distributing lone pairs. So this oxygen needs 6, 2, 4, 6. And this oxygen needs 6, 2, 4, 6. Altogether, I've distributed 2, 4, 6, 8, 10, 12. All of my electrons have homes and I have nothing left. However, when I go to do my octet and duet rule check, I see that oxygens are happy, but carbon has only 4 electrons that it can claim. So this is going to be a problem. When you run into this and you want more electrons, but you don't have any, multiple bonds become necessary. So what happens is this pair of electrons, this lone pair, I'm going to cross it out, they become a bonding pair. And then this pair becomes a bonding pair. And now I have this structure. Okay, I use the same number of electrons, but now I have multiple bonds. My oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. And this carbon has 2, 4, 6, 8. I hope that helps.